evening, sir.
Renema.
Can you wait for some minutes, sir?
Yeah.
50% of the participants have joined so far. Just 2 more minutes we'll wait and then we'll start, sir.
So now some noise is there. Ma'am, is it so?
Is there anybody else who unmuted? So there is some noise from your end, sir. Is it, sir?
Is it okay now, ma?
Okay, sir.
Oh, while talking, it's
That is
fine.
actually fine. Now
Okay,
I have to sit it.
Okay, Jennifer, you can start.
Yes, ma'am. Good evening, ladies and gentlemen. Welcome back to the third day of the 3 days online workshop on X-ray diffraction. I hope you all had a wonderful weekend. And before we move on to the technical session, I invite Dr. Jemima Balaselvi to invoke the Lord's name. Ma'am, you're on mute.
Let's all play. In Bible, Proverbs 16:3 says like this: Commit your work to the Lord, and your plans will be established. So in this promise, we seek the Lord's guidance for today's workshop. Let's pray. Almighty and everlasting Father, we have set many goals for ourselves. We want to achieve academic greatness and success. We know this goal will not fulfill itself overnight. It will take hard work, determination, and a fixation on your greatness and support. Please prepare us for this lifelong journey towards academic success. Lift us from our failures and celebrate us in our victories. Excite our mind for tomorrow. Please join us in this path towards success. We ask all these in Jesus' precious name. Amen.
Amen.
Thank you, ma'am. Now I invite Dr. Johnson of the Department of Microbiology to introduce the speaker of the day. Dr. Johnson.
Good evening. I'm glad to introduce the speaker of the day.
Sir, 1 minute.
Dr.
Excuse me. I think Israel, sir. Israel, sir.
Yes, ma?
Your speaker is having some echo effect, sir.
Let me see. Is it all right, ma'am, now?
Not yet.
Hello?
Still
Not
there
yet.
is, maybe you have to switch off your speaker since you're using the headset.
Is it okay now?
Right, okay. But when we are speaking, no, there's an echo coming. Okay, sir, okay.
Yeah.
Introduction about the speaker. A warm greeting to everyone. I hope I am audible to everybody. Am I audible?
Yeah.
Yeah.
Yes, sir.
Speaker for this second evening is Dr. Sushmit Samuel, currently Assistant Professor of Physics at the American College. He had his bachelor's from the American College in Physics and his master's in Physics from NMS SUM College of Madurai. Then he went on for his master's in philosophy from NTU, where he also did his doctoral research, and thereafter he has served as a lecturer in physics in various pioneering institutions like NMS SUM College and Christ Church College in Kanpur. His areas of interest are crystallography and crystal structure, charge density in semiconductors and magnetic semiconductors, pharmaceutically important materials, and the analysis of charge density and the topology of materials, quantum chemicals, nanomaterial preparation and characterization of the same, and so on. He is a life member of Indian Crystallography Association. His notable achievements are he has been awarded by the Defense Secretary as a commendation for outstanding leadership in NCC for the year 2014. All of us, we know him as the NCC officer who walks around the college with his tenacity, and he has got 60 publications to his credits, and those are into focused journals which have national and international circulation. And now he goes on to demonstrate his interest in crystallography. Sir, with this brief introduction, I welcome you. Over to you, sir. Please.
Yeah, thank you. Thank you, Johnson, for the wonderful words. I'm really delighted to be among you all, and I'm really happy that I'm going to present this for an audience who are expected to be, of course, to know some of the things about the crystallography and so on. Okay, so the prerequisite for this particular session is actually you should have some kind of a basic knowledge on X-ray diffraction, and its theory, so that of course you can actually use that idea for selecting a particular software and tool for your own analysis. Okay, so this is not actually for a particular analysis, but of course this is actually for an analysis that you are actually interested in. Okay, so it's not like any other the imaging technique where of course like an X-ray image that we do actually in clinical understanding, where actually you can just see those X-ray films on the screen, and then of course you can actually interpret them, okay, by your own eyes. But then of course the X-ray diffraction analysis is completely different. What they see, the X-rays, what they see is actually a real artist, and then what you get out of the X-ray diffraction experiment is actually an information on the Fourier space. Okay, so it is a completely transformed space, and therefore you need some softwares and tools by which actually you can interpret those X-ray diffraction pattern, and then of course you can go on further. okay, to understand what it is, what are all the information that actually you can gather out of the X-ray diffraction pattern and so on. Okay, so this is actually the thing that actually we're going to talk on. Okay, so I'm actually going to introduce this thing, but then of course let me start with the definition. X-ray diffraction. You know about X-ray diffraction at least for the past 2 days, or for the first 2 days of this workshop. Actually, you have known. Actually, you came across all this information. So let me just recollect everything for a short while, and then of course let me pass on to what I was actually asked to do, and I'm interested to do. Okay. So the X-ray diffraction is basically a non-destructive analytical technique that provides detailed information on internal lattice of crystalline substances. So this is actually for internal matter, basically something that cannot be seen by our naked eye or by any other microscope or anything like that. Just, the topology can actually be seen by the surface electron microscopy and other things, but then you cannot see what is inside. So to see all the things inside, of course, you need X-ray and X-ray diffraction. So this is actually a geometry. So where actually you place a crystal in the middle, and then of course you have an X-ray tube that actually passes on the X-ray beam. The screen actually filters out, or you can say it monochromatizes or collimates the beam, and then of course one particular wavelength is allowed to fall onto the crystalline solid. Then of course the crystalline solid is actually having a lattice like this, okay, where the atoms and molecules are arranged in a very systematic periodic manner. Okay, you should remember that they are not random arrangement, they are very systematic and they are very periodical. So the thing is, once when they are periodical, then only of course we call them as crystals, because the basic definition of a crystal requires, okay, the atoms to be in a periodical arrangement. Okay, so that is the first thing. Okay, once they are there, every single plane of lattice, okay, can actually act like a diffracting plane. Okay, so the thing is, these planes can actually diffract, and those diffraction can actually be seen in the form of dots here. Okay, so the thing is, these planes will diffract only when they obey the Braggs law, which is what we call, of course, which is 2D scientific as equal to n lambda. You know about what is actually the thing. Of course, we must have learned the things, of course, in the past, in the last 2 sessions. Okay, so you get the sparks from the diffracted X-rays, okay, on a photographic plate, which is a very old technology. But then right now, actually, we have counters and we have sensors. Okay, we have CCD devices, charge coupled devices, and so on, which can actually count these the X-ray photons on a particular spot. Okay. So this is a basic arrangement of X-ray diffractometer. So this is actually the detector. Okay, you can say the counter, photon counter, X-ray photon counter. This is the X-ray tube. So the collimator is there, the crystal mount is there, crystal is placed here. The X-ray falls onto this crystal here. Okay, then the counter actually detects. Okay, so then once you get the information, okay, out of it, okay, then of course what you have to do is you have to interpret this X-ray diffraction pattern in a way you can understand the properties of the crystals. Okay, the properties of the solid that actually you are actually using for analysis. Okay, so the single crystal X-ray diffraction is the most commonly used for precise determination of crystal solution. When we say solution, it gives you the complete geometrical arrangement of atoms and molecules. Okay, remember they are very, very important, because the way in which actually we can distinguish different molecules is actually by means of looking at the atoms, because you know in an organic solid, everything is carbon, hydrogen, nitrogen, and oxygen. So the thing is, the way in which they are arranged, okay, and the number of ways in which they are arranged, they actually give you different molecular formula and different molecular structure, and you can actually understand all those things in a different way. I mean, when you look at the polymers, when you look at the polymorphs, when you look at the polymorphs and different forms of the molecule, then of course actually you can understand how they are actually geometrically arranged and how they differ from each other. Okay, so that is the thing. So solving all these things is actually what we call crystal solution. Then of course, as I said, of course you can understand new minerals, new molecules, then the molecular structure, crystal properties and molecular properties. See, the thing is, you can actually calculate the crystal properties, many different properties. We'll talk about all these things in the later session, okay? And those properties are very, very important in a way. Actually, you can understand these molecules in a better way, okay? Then, of course, drug-related information, where actually the drug engineering requires so many information from a molecule, and those information can actually be gathered from the X-ray diffraction experiment. Okay? And not only that, actually, we physics people are interested in understanding the electric property, optical, magnetic, dielectric property, and so on. And as a bonus, of course, you can actually get a Nobel Prize also. Okay, so this is a man, Venkatraman Ramakrishnan, of our own origin. Of course, he received the Nobel Prize in chemistry in 2012. Of course, what he did was actually he explored the atomic structure of a ribosome and our chromatin structure with the help of X-ray crystallography. It was a very interesting story. 8 different groups of people actually were determining the structure of their own domain. Okay, so what they did was actually they have divided the whole crystal into 8 different domains, and then each domain was actually solved differently. Then they came together, they put everything together to form the complete structure of a molecule, ribosome molecule actually. So it was a protein molecule. So the molecule is a very, very big. We call them as a macromolecule. The size goes over many hundreds of angstrom in every single direction, ABC direction, and then of course putting everything together and then of course forming a single structure is actually very challenging one. Their group actually did, and he got the Nobel Prize. Okay, so crystallography can give you a Nobel Prize if you are really interested in, and then then the strength of X-ray diffraction analysis, X-ray diffraction. So there's no separate standard. You can't compare. This is actually what you get out of everything. Like an X-ray image of a broken bone. Okay, there's no standard where you can compare the one with the other one. Okay, your bone is your bone. The figure that you get is your figure. So there's no other figure that actually with which actually can compare of. So likewise, actually we have the X-ray diffraction, which is the standard one. So you can't compare it. It's non-destructive as you said. So other things are there. Okay, you can actually get every detail of the crystal structure, bond lengths, bond angles, type of bonding. Okay, we'll talk about all these things. Okay, determination of crystal chemical controls on mineral chemistry. Okay, so not only that, of course, you can actually put a crystal into different pressure situation and the temperature situation, and you can actually see how the phases are actually changing from one form to another form. Okay, so phase transition can also be can be watched, okay, of course, with the help of the X-ray diffraction. In the case of phase changing, okay, phase transition, so which atom actually plays a major role, or which set of atom actually plays a major role in changing the entire structure of a molecule. So all these things can actually be seen. Order patterns can actually be derived. So that is actually one of the things. Actually, when somebody is interested in powder patterns, not everybody is good at a single crystal diffraction. Some people are actually good at the powder diffraction. They can actually use it and things. Okay. Some limitations are there. Okay, so you need to have a very good stable crystal. So volatile, fragile, something that can actually go out. It can suddenly disintegrate. So kind of a chemical actually cannot be used actually here. So the thing is, you need a stable crystal. At least it should remain stable. Okay, it should not go bad. It should not be fragile. It should not break down. Actually, at least till the experiment is over. And at least you need to have a crystal of 50 to 250 microns. If the bigger the better, but not the bigger one. Okay, so you need to have somewhere in in the sub-millimeter size. Okay, optically clear, we can't have a polycrystalline sample. You have to have an optically clear sample. So thin samples can be handled with a very difficult. It's very difficult to have a twin sample. Okay, data collection actually requires somewhere around 24 to 72 hours. But with the latest technology, with the CCD camera and so on, very volatile compounds like protein compounds, some virus, bacteria, and all those things can actually be recorded within a minute or some. So actually, within a very short period of short span of time, and they can be recorded. Okay? So it's like shoot and think later, something like that kind of a technology that people actually use. Okay. So this is actually the single crystal data collection. So the data collection, you see all these parts here. These are all actually real picture, the photographs of a single crystal diffraction. Okay. So these parts actually give you an intensity. Okay. So the photon counts that were counted for this particular angle, at a particular angle, at a particular spot actually gives you intensity. So basically, every single spot actually will give you information on the particular plane actually that it comes from. So HKL plane, the Miller indices will actually be found out. Then of course the observed intensity and any error, any possible error that comes from instrument, experiment, and so on. So that will also be recorded by the computer, okay, for every single reflection. And this intensity can also be transformed into the structure factor, okay, by means of a Fourier analysis by a computer and so on. Okay, so what we can do actually is every single dot in X-ray diffraction pattern will give you information on the intensity, okay, and of course which can be further used for understanding what is there in a particular plane. Okay, so remember, every single intensity spot comes from a plane, not from an atom. It comes from a plane. A plane will actually have a set of atoms, a large number of atoms, or some over some Armstrong units. Okay, the size with the sizes of 5 Armstrong in each direction. This is actually powder diffraction geometry. So where actually we'll have a sample. See, why we need a powder sample is many of the chemicals cannot be crystallized. So they cannot be made into a solid at room conditions. So that is actually very, very important. Because in room conditions, in normal conditions, of course, they cannot be in the crystalline form. So they can only be in amorphous form. So we need to have powder diffraction also. This is again the geometry. So data recording technique, actually, I think Dr. Sarnadhar actually must have talked about all these things. Okay, so the data is recorded over a range of 2 theta in steps. Okay, and they are recorded like this. Okay, so in the case of powder data, of course, they are recorded as peaks, as a profile. Okay, as a two-dimensional profile like this. Okay, so actually you can see the profile actually goes between the 2 theta, the x-axis, and the arbitrary photon counts on the other axis. Okay, so 2 theta and intensity. So every single intensity from every single angle is actually recorded. Okay, and they are continuously recorded over a long range. Okay, then of course put in a profile like this. Okay, so you will actually have a 2 theta intensity and the error that comes along with the intensity. Okay, for a powder diffraction, there are several types of data formats, we call them. Okay, the formats are primarily because of the companies. Okay, so the scientific companies, so they're not saying they don't have a universal formula by which actually they record it. They have a different format. Maxine, Rigaku companies, Systronics, Siemens, Philips, then many companies, they'll all have a different setup and they'll have okay. Now, once the data is recorded, the data should be reduced. Okay, data will be analyzed or refined. So for any possible errors, okay, due to experimental settings, there may be many experimental errors which comes into play, electronical errors and everything that is that comes along with the instrument. Okay, so instrumentation error is also there. In optical error is there. Okay, all those things can actually be defined and they can be removed from the data. Okay, so they can be removed from the data. Then there is a crystal absorption. So it depends on the thickness of the crystal. Okay, some of the X-rays can actually be absorbed by the sheer thickness of the crystals. Okay, extinction effect is basically because of the multiple reflection that comes from the stacked planes, H-scale planes in the crystal. Thermal diffuse scattering is primarily because of the temperature effect. Okay, even at room temperature, the atoms are vibrating about its mean position, so they are not stable. They are actually moving along a particular axis. Okay, or in a three-dimensional way. So they can have any number of freedoms. Okay, so they can actually so those vibrating atoms will diffuse, okay, the incoming X-rays. Okay, so that will also affect the intensity that is recorded. Then fluorescence effect. Okay, when they have crystals of similar type, okay, like that of the target X-ray target that you are, like for example, suppose if you're using a copper K alpha beamline, and if the molecule is actually having a copper atom inside of it, okay, then of course they'll have a fluorescence effect. So the energy that comes out of the copper K alpha, actually copper K alpha actually is the innermost electron gets excited, and because of the excitation, actually you get this X-ray beam, okay, copper K alpha. So the same energy, okay, the same X-ray can again be used for exciting the innermost electron of the copper atom which is inside of the molecule. So there can be fluorescence effect also. So those things can actually be removed. Okay. So we need to have softwares to do every single step. Okay, all the entire thing. Okay, so it depends on. Now then, after that, once you reduce the data, then of course you have to go for structure determination procedure. If the structure is not known previously, the crystal is a new one. Okay, so there is a definite procedure that is adopted for so long years. Okay, so you can use them, or you can directly use the software even without knowing what it is. Of course, you can simply go into the software, you can run the software, you can get out of it with some results. But then, of course, you should know what is actually going on inside of it, and then, of course, then only actually you can interpret those results. Otherwise, the result will simply be a number or something. Okay. One of the most interesting and the most difficult, okay, remember, is the X-ray diffraction in biology. Okay, where actually we use the biomolecules. So biomolecules are they are termed as macromolecules basically because the size of the unit cell itself will actually run over several angstroms. Okay, from suppose normal organic molecule or a normal inorganic molecules will actually have a very small unit cell. Okay, so less than 10 angstrom. Okay, less than 10 angstrom for a site. Okay, so 10 by 10 by 10, so 100. 1000 angstrom cube. Okay, will be the maximum possible volume for an organic, the inorganic structure. But whereas when you go for organic structure and when you go for biomolecules, the size is going to be very high. So one side actually, if the length of the unit cell is 100 angstrom, so you multiply 100, and then 100. So basically 100 cubes to volume of the entire unit cell. So you will see many different molecules are inside, and the atoms inside will be a very large number, and therefore the mathematical complexity is increased, the computational difficulty is increased, and therefore it is very challenging. That is why you get a Nobel Prize. Okay, so what you do is actually it's actually what we call protein crystallography or macromolecular crystallography. Okay, there are methods, okay, by which actually you can solve these the molecules, okay, then you can actually come out with a raw answer. These are some real photographs of protein molecules crystallized. These molecules are very, very small, microns, okay. You will see, okay. So then now, okay, let me go for the topic of the day, and it's actually softwares and tools for XRD analysis. So what I'm going to talk from here on is basically a drop in an ocean. Basically, I'm going to concentrate only on a drop in an ocean. So if you know the ocean, you better swim on your own. But I know only about the drop, so I can only talk about the drop that I know. So the things that actually we have come across and we have used in our one the research period. Okay, so for the past 20 years, I think we've been using several softwares, okay, which are primarily free. See, we can't afford to buy a software for thousands of dollars, so that's not possible. So you go for some free software. So I'm going to talk more on free softwares than the commercial softwares. Okay, now the produced primarily by the top X-ray diffraction companies, Bruker Corporation, the Gaku, Sun Analytical, Philips is there. Yeah, okay, so X-ray and optical systems, proto manufacturing, Bruker, Siemens, everything is there. So they are producing their instrumentation. Along with that comes the package of their own software. So you can actually use them when you are buying an instrument. Okay, you get a software free. I mean, not free, but of course they'll add money to that, and then of course actually you can use it. Okay. The other softwares are the free softwares. Okay, other softwares are free software which are available in the internet. Anybody can go there and you can download it and you can use it. Only thing is they will ask you to acknowledge them, okay, the authors of the softwares, okay, in your publications and so on. Please do that. Okay, please don't neglect that. Okay, so that is actually a crime because when they are free, okay, so I think it is better we acknowledge them. Okay, whenever we use them. Okay, so that is actually one thing. Then some of the softwares are license-oriented softwares. What you have to do is you have to write mail to the authors, and then of course you get the permission. So they'll give you something like an OTP, okay, something like an OTP or a password, so that actually you can unzip the zipped file of the entire software. Some softwares are open. You can modify the code. You can send them back, but then every time, of course, every time you get the permission from the people, or you acknowledge the people. So that's actually very important. Okay. Now, the parameters that you can actually get from XRD, okay. So, as I said, molecular structure for which actually you need cell dimensions, atomic type, okay, bond distances, bond angles, thermal parameters, okay. Then lattice properties, a strain in the lattice, whenever there is a doping or some unwanted thing happens there, when you are doping by another foreign atom, or when there is a vacancy in the lattice. Okay, so a strain actually happens, so that can actually be seen. Texture of the lattice can actually be, of course, understood. So bond concentration, vacancy. So then chemical properties, bond type. You can actually think about any different type of bond. Okay. So starting from hydrogen bond, ionic bond, the van der Waals bond, it's a covalent bond, and the intermediate bonds. Okay, so the polar covalent bond and things like. And we have actually come across this strong correlation, which is another type of a bonding. Okay, it's not exactly covalent type. It is actually much more than covalent type, where there is a strong correlation between electrons of the f orbitals. Okay, so there are elements, okay, which actually show those kinds of bonding type. Okay, so we have investigated some of them in our own research. Okay, so you can actually the pi bonding, sigma bonding, all types of bonding can actually be understood from the X-ray diffraction. So that is what I'm trying to say. Okay, So it is not only the other tools. I think you are using what is it, FTIR and the magnetic resonance, MRI techniques and other things to understand the bonding type and other things. But here, of course, NMR, sorry, not FR, NMR. NMR and the FTIRs are basically other tools by which actually you can understand the bonding type. XRD can give you very good detail actually about the bonding type that exists in the crystal. Okay, bond strength, every single bond and its strength can actually be measured. So I think the other, I don't know whether about the other tools like NMR and FTIR, but then of course bond strength can be measured here. The charge density around an atom can actually be mapped, and then of course you can understand the chemical nature of the molecule. Okay. The experimental ground state properties can actually be understood, which can otherwise be calculated only from quantum mechanics. So it is actually a complementary tool for the quantum chemistry. Okay. XRD is actually a complementary tool for quantum chemistry, so people should understand this. Then, okay, so the other properties that come along with that. Okay, one electron properties. Okay, so which are all quantum chemical properties. Okay, drug potential, again a quantum chemical property, electrostatic interaction energy, intramolecular interactions, and you can actually see intermolecular interactions also. Okay, to start with, suppose if you are interested in, if you want to know what is actually the crystallographic software, please go to this page, and then of course I think I have opened another page. Sorry. Okay. Yeah, here it is. Okay. So this is actually a crystallographic software list. Okay. So you have a crystallographic software list. It starts from A to Z. So anything, if you want to start some software that starts with N, then of course you can start with the N. Okay. So or Z. Okay. Suppose if you are interested in Z, you can go for Z, and like that, actually you can go for anything. Okay. So there is a code museum, crystallographic code, source code museum is there. You can go there, you can download the code, and you can use it on your own. Okay. And as I said, of course, you can actually see any crystallographic software. Okay, from the IUCR International Union for Crystallography web page. Okay, so they are a very big organization. Okay, so I know them since my childhood of my research. Okay, so there are back volumes. Okay, there in Madurai Comrade University. We used to search for it, but now they are there, of course, at the tip of your fingers. Okay, so you can simply go to the page and then click for it. Okay, then of course you get it. Okay, so that is how actually it's very simple. So some of the free softwares which are used for single crystal refinement. Okay, so when I say single crystal refinement, the crystal should be a single crystal. Okay, then the refinement technology, procedure is actually some standard procedures which are available in crystallography, which are used by these softwares. Okay, so the first and foremost is Selectshell. Selectshell is a very old crystallographic software. Okay, we were actually even using the magnetic tapes actually of Selectshell. We used them, of course, in Madurai Comrade University in the 90s. Okay, so in our own research, when we were doing our own research, then people are actually using it. Those days are the days when you get a 5 structure, and then of course you submit your PhD thesis. Now 20 structures can actually be solved in within 4 or 5 years. Okay, of course if you get a good crystal and so on. So this is actually the web page actually where you can actually just click on the thing if you go to that. Okay, then of course there is a JANA 2006. Okay, this was the one actually which was helping us because we were using inorganic materials. Okay, so those materials are known for long time, and then of course actually we can, once the structure is known, of course it's very easy to go with the flow of this JANA 2006 software. Okay, then there is a WinGX software. Okay, which was developed by a scientist called Luis Farriga. So he's there. Okay, of course, all you need to do is write him. Okay, by mail, of course, you get a signature from him, and then of course you can use it. Okay. Then there is another software, SIR 2014. Okay. The SIR software was originally used along with the Excel. Okay. So then it's a very old set of softwares. Okay, you can actually now they have developed it further, so they have tested at least until 2014, where actually they have incorporated so many things in the software from which actually you can derive so many parameters. Okay. Then there are other parameters. Suppose if you are interested in suppose if you are interested in just solving unit cell constants, because you can simply use this unit cell constant instead of going into this, preparing a very big input file. You give some small number of input data, and then of course you get the unit cell information out of this. Okay. Cell refinement software. Space group software is one of the helpful software which can be used for any purpose to get the symmetries and other things. Of course, suppose if you want to place an atom at one point by means of a symmetry, you can use the symmetry cards of the space group software. You put that position there, you get a symmetry position there, then you take the atom in that symmetry position, you put it there, and then of course you solve it. Okay. So this is actually the Excel manual. Okay. It is actually a very old manual which came in the printed form. Otherwise, you can see all these manuals are there in the website itself. Okay. So this is actually the kind of the input file. Actually, you give you the wavelength. Okay. So ABC is the size of the unit cell. Alpha, beta, gamma angles that you have used. Okay. These symmetric cards are basically, as I told you, these symmetric cards can actually be gathered from the space group software. So if you don't know what are actually the symmetric cards, you can go to the symmetric cards. Okay, you can go to the space group software. You just type in the space group, okay, or the number. Okay, you type in the space group or the number, then of course you get all the cards. Symmetric cards. We call them cards. Symmetric cards. Okay. Then of course the possible atoms. Okay. So carbon, Ag. Okay. The gold, arsenic, fluorine, nitrogen, sulfur, and all those things. Okay. So then of course I think they are the valence, or I don't know. Okay. So I think I'll have to look into the manual for this. Okay. So like that, actually you can actually enter all the factors here. Okay. Then the positions here. The silver actually Ag is at origin. Arsenic is at some other position. Sulfur 1 is there. Sulfur 2 is there. Carbon is there. Nitrogen 1 is there. Fluorine 1, fluorine 2, and all those things. Okay. So once you fix up all these atoms to start with, remember, you cannot start everything from zero. You have to give some positions by assuming, okay, the possible structure for a molecule. See, without a possible structure, you cannot actually start. You have to have a starting point. So for that, actually, you need to know some chemistry. You need to know some chemistry. You start from there. Okay. So you need to have some. Once you get started in a right way, then the refinement, of course, you'll get refinement, possible refinement very soon. Otherwise, of course, it will be very difficult. Okay. Then there are cookbooks available. There are cookbooks available, actually, like an ordinary cookbooks that are available for our own cooking. Tenindia Samayal, Vada India Samayal, Chettinadu Samayal, cookbook. Cookbooks are available for almost all of the software. Okay, so you go for any of the software here. So Zana 2006 cookbook is there. So where you will see every step. நீங்க ஒண்ணுமே செய்ய வேண்டாம். நீங்க நம்ம ஊர்ல நம்ம சொல்ற மாதிரியா கடுகு எடுத்து அடுப்புல போடு எண்ணெய் எடுத்து ஊத்துன்ற மாதிரி கிட்டத்தட்ட every single step is actually explained there in the cookbooks. Okay, so please go through the cookbook. Okay, Of course, it is going to be very tiresome, but then of course you have to go through it. Once you master it, then you will not be in need of cookbooks. You can do it on your own. Okay. So the WinDX program, as it is, okay, it's a very good program that is used for atomic structure determination. Okay, of course, crystal structure determination. So Professor Luis Ferreira we were actually delighted to have him as a chief guest on one of our own workshop here at the Department of Physics. So this is actually Dr. Ferreira. He was with me. We were discussing our own research work, and of course he was appreciating. Okay, so that is actually one of the things. Of course, again for 2014 manual is there available. Of course, you can actually use them for everything. Okay, so see, most of the softwares are self-explanatory. I mean, suppose when you look at the icons arranged here, every single icon will be arranged by the steps. Basically, the first step you start from here. Then the next step you go there. Next step you go there. Next step go there. Okay. So they are primarily self-explanatory. So you can go through the menus of all these icons. Okay, the icons there in the toolbar. Then of course you can see actually what actually we have to do. So that is where actually you have to have some ideas on crystallography and chemistry. So once you know what actually they are asking, what they are actually asking you to do, you can do it. You can simply enter the type of atoms that are involved in the molecule. You can actually simply tell them how many atoms of a particular, how many atoms are there for a particular atom type in a particular molecule. For example, how many carbon atoms are there in a ring. Okay? So that you can actually define. Okay? So where do you put the oxygen atom? Where do you put the hydrogen atom? Which position is the hydrogen atom is actually supposed to lie? Okay. So because fixing of hydrogen atom is actually very difficult. So unless you know the chemistry of it, okay, you will not be able to do that, because the X-ray diffraction does not care about any atom whose electron density is 1 and less than that. Okay, so that is not possible. So happen the hydrogen atom is having electron density as 1, so the total number of electrons is 1, so it will be very difficult. So now I'm showing these are all some of the real mapping of proteins. Okay, so what we have here is a plain protein. All you have to do is you have to add some colors to it, and then of course from every single colors and every single square, you'll have to identify the pattern of the atoms there. Then of course the chain of atoms, the chain type, and then the atoms inside of it have to be understood. See, so this is actually a very small square here. You cut this small square here. So this square is actually giving you the F square here. So this is actually a small square which is expanded here. So this is actually a small rectangle here which is expanded here. So where there are many atoms. So likewise, actually there will be many atoms for a complete protein. One protein molecule is actually a one protein molecule, and the image of it actually will look like this. This is how actually you will actually get the imaging. Okay. So this is actually the potential, the electric potential imaging of a protein molecule. Okay. So where actually you will come across the electrophilic and the nucleophilic regions. Okay, the electrophilic and nucleophilic regions, which are basically the regions where they attract and repel the electrons, basically. So okay, they attract the electrons and they attract the negative charge ion and the positive charge ion and things like that. Okay. So I think the chemistry will be good at saying all those things. Okay. Now, all you have to do is, once you get the protein structure here, you have to identify them whether it's a new one or an old one. Okay, from the other tools like CS23, DE 2.0, process, predator. Okay, And then of course, so all these things are basically a repository of protein structure, okay, protein structure, okay. So some are actually using the X-ray diffraction techniques also. Some use NMR techniques, okay, and some use FAR technique, the IR techniques, and so on, okay. So the thing is, all you have to do is you get the protein structure, and then of course you can compare them with the repository, okay, whether the protein that you have found out is actually a original one or anything new, okay. So, but before that, you have to be very careful that you have completed the entire refinement, okay. So that is actually the most challenging part, okay. Now, some people are interested in powder crystallography. Okay, so when I said, as I said, when some of the materials cannot be formed into the into crystalline form, okay, so at room temperature limit, okay, or at room conditions, okay. So in room temperature and atmospheric pressure conditions, they cannot be formed in crystalline form, so that so they are in the powder form. So once they are in the powder form, okay, then of course you can use all these things. Okay. Remember now with the advent of the nanoparticle system, most of the nanoparticle system are in the powder form. So the thing is, for all the nano structure and its determination, okay, I think we have to use these softwares. Okay. So there is a foolproof Expo 2004. All these softwares are there. Okay. There is a breadth software is there, okay, which can actually find out the breadth of the profiles and other things. So there's a grind software is there, which can actually determine the grind size of the nanoparticles. Okay. Now the match software is one thing actually by which actually you can match your own profile with the known profiles. Okay. Your own known profiles. Okay. So you can actually see, actually you can input the file, and then of course you can actually select the type of atoms involved in the material. So once you select the type of atoms involved in the material from the periodic table, then of course it will list down almost all of the molecules, okay, which are having the combination of all the atoms that you have actually selected. Okay. So once the selection is there, then it will match your data and the data which is already there in the repository. So the thing is, once there is a matching is found, okay, then of course it will give you a matched profile. Okay. So if the matching is not found, then of course it will say, okay, so your data is a new one. Okay, you can add it into a repository, or you can actually use it on your own. Okay, the companies, the industries which are producing new materials, they don't go with the repository. Okay, they use it, but they don't deposit their data. Okay. So this is actually a matching software, okay, it's a phase matching software. So you can match the phases of your molecule and the molecule which is already there. Okay. So when you have a doubt, okay, so you can actually use it, okay, to match it with the one. Okay. And this is again another software actually where actually you can do full refinement. When I say full refinement, you can actually start from the unknown structure. Okay, and then of course you can select the type of atoms involved in the structure in the molecule, and you can go for the entire structure prediction with this data. Okay, see the methodology. Okay, with this actually you can find out the we can do the refinement. Okay, it's available in the YouTube. You go watch these YouTube videos. Okay, so side by side, of course you can. You can watch the YouTube, and then of course you can use the software, and then of course you can do on your own. Okay, so match software is there in the YouTube, foolproof software is there in the YouTube, not every software. Okay, so there is another software called Expo. Okay, so Expo will invariably predict the chemical formula and the chemical structure also. Okay. So it will actually predict all the bonds here and the bond lengths, and not only the bond lengths, of course, the bond critical points also. Okay, so bond critical points, bond paths also. Okay, some of the bond paths which are not straight line. Okay, which are bent. Okay, due to the arrangement of atoms in the molecule can also be seen from the expose software. Okay, so now this is actually one of the YouTube video from which actually you can calculate the crystallite size from XRD data using Origin. Origin is a commercial software. Okay, you can get pirated one also. Okay, so you can actually determine the crystallite size. Okay, of the nanomaterials. Okay, nanotubes, nanoballs, and other things are there. Okay, you can actually find out. Okay, there is another code called grain. Okay, which was actually originally written by Dr. R. Saravanan. Okay, actually we used to write photon codes, okay, for our own calculations, okay, in the 90s, and we execute them. Okay, so we were doing it. Okay, alongside, of course, our guide actually Dr. R. Saravanan of Majora College. He was actually doing all the other calculations also. Okay, like when you know the theory, of course, you can write them, of course, into codes. Okay. So once you can actually, again, they are there in the crystallography. See, they are submitted in the IUCR software list. So they are free. You can go to the website. You can download it. You can use it. Just acknowledge. That's it. Okay. So actually, you can find out the crystallite size and strain. Okay, of the lattice from the software. Okay. So this is actually one of the useful software for nanoscience people, or people interested in nanoparticles. Okay, and this is actually another a simple powder diffraction software. Okay, from which actually you can calculate, you can actually refine the cell parameters. Okay, so the thing is, you can simply you can download this one from the IUCR website. Okay, so all you need to do is, of course, you just give the input file as the intensity input file, just straight from the instrument. Okay, it will automatically do. As I said, every single toolbar here, okay, is arranged so nicely. Okay, so that you can do it one by one. You click this one, then you click this, you click this, you click this. Then ultimately will end up with the final answer. Okay, so you can actually take a powder profile. You can match them. You can index them. Okay, you can index them. You can assign HKL values for those. Okay, then of course you can start with some cell parameters, and you can refine them along with the profiles. You can find out the exact TADC values for this one. You can start with these values. Okay, and then of course you can go for crystal refinement. Okay, so these are all some starting softwares you can see. Okay, Origin, okay, as I said, it's a commercial software which can actually be used for many different things. Okay, so there's a software called Edit Plus. Okay, you can actually column edit. Okay, so ஒரு particular column மட்டும் அப்படி edit பண்ணணும்னா edit பண்ணலாம். Okay, you can cut down the whole thing. Okay, you can leave the rest on the left hand side and the right hand side. மற்றதுலாம் நீ அடிச்சன நீ கட் பண்ணனா எல்லாமே திருப்பி அலைன் ஆயிடும். அந்த மாதிரி எல்லாம் இது அப்படி கிடையாது. ஜஸ்ட் ஒரு காலம் மட்டும் அப்படியே கட் பண்ணி எடுத்துடலாம். அது அப்படியே பிளாங்காவே நிற்கும். So that can actually be done with the help of software called Edit Plus. Now it is commercial. Okay, now it is commercial. Origin is also commercial. Okay, so these are some utility. Okay, okay. Visualization softwares are very, very important because once you produce some good pictures, okay, so visualizing them is very, very important. Okay, so ARCUP software is there. This is a very old software. Okay, Mercury, I think the chemistry people must have been very familiar with Mercury. Okay, you can do many things with the Mercury software. Balls and sticks are there. Okay, this is actually a software which is used for unit cell shape size. Okay, crystal shape. Okay, you can actually have crystal shapes and so on. Okay, Vesta is a versatile tool for visualization. You can actually visualize many things, starting from a molecular structure, unit cell. You can go for charge density. You can go for electrostatic potential. You can actually do gradients of electrostatic potential and so on. Many things you can do. There are many things, of course. You can convert the data into many other quantum chemical parameters also. Okay, what you have to do actually, you have to have a file of charge density. So once you have charge density, of course, you can make them into other parameter file, okay, quantum chemical parameter file like kinetic energy density or electrostatic potential and so on. Okay, so VESTA is very useful. Okay, I'll show some of the screenshots. Okay, then there are charge density software. We were privileged to have a workshop in IISc with legends, of course, okay, on charge density. Okay, so WinXT software is the MoPro software there. Okay, so Philip Collins was there, a legend in charge density studies. Okay, Christian Gels was there, Benoit was there. Okay, so many other people. Okay, people from all over the world. Okay, I think we really enjoyed. I think myself and Dr. Anslin were there for the workshop, okay, in IISc Bangalore and the solid state chemistry unit. Okay, so these are all the charge density software, WinXT and MoPro. The G-Fourier was the original software, okay, but then of course it was using Fourier techniques, okay, but then the WinXT and MoPro are using multiple techniques. Okay, so if you have heard of multiple techniques and so on, there is WinX Pro software is a very versatile tool. As I said, you can actually calculate the parameters which can otherwise be calculated only with the help of quantum mechanics. So as I said, it's a complementary quantum mechanics software. Okay, so we have, as I said, X-ray diffraction technique can actually be a complementary for quantum chemical determination of various parameters. Okay, so XRD is not a simple one. It's very precise. You can use it in a very precise way. Okay, so when I see, I'm really saddened by the factor where actually people see XRD down and they don't understand what is actually inside of it. There are plenty of information in XRD. Okay. So RTOP is actually the visualization software. It is RTOP. Okay. Ellipsoid diagrams can actually be drawn. Okay. See, ellipsoid diagrams are basically to understand how the freedom, how the freedom of the vibrational degrees of freedom can actually be understood from these softwares. Okay, how the edge atoms are actually vibrating. Okay, and also the atoms in the middle. Okay, so how they are vibrating? What is actually the vibrating amplitude? So you see O3 and O2. So the size of the amplitude here and size of the amplitude here is different. The size O4 it is different. So you can see distinguish the freely vibrating atom and the constrained atoms. Okay, so like that actually you can see many things. Mercury, as I said, you can have a molecular structure. Inside of it, you see molecular structure. You can have atomic structures. You can have a unit cell diagram. You can have planes. You can draw crystal shapes. So you can actually predict the crystal shapes. So when you are growing a crystal and the crystal grows like this, you can simply say your molecule and the shape that you have seen. You can take the photograph of a crystal. You can see the shape that is predicted by X-ray. Then of course you can show them, of course, in your publications. Okay. After that, the crystal shape again can be predicted. The molecular diagrams, the planes, okay, in charge density. This is actually ESP. Okay, electrostatic potential can actually be there. So it can give you variations between the electrophilic and nucleophilic regions. Okay, in the blue region and the red region. Okay, where actually they attract the negative charged ions and positive charged ions and so on. Okay, so these are all the simulations from. Okay, so these are all basically the structures from VESTA. So a plane and the charge density can actually be seen. See, when you look at the charge density, people like us, when I say people like me, people like Dr. Anslin, we have a group of people actually working on the charge density. We can actually identify what is actually what. Okay, what is actually happening there. We can see lone pair region, we can see bonding, we can see covalent charges, we can see valence region. we can see the depleted region and so on. Okay, but of course, starting from there, of course, nobody can actually see that. But once you get the experience of it, I think you will be able to understand what is actually what. Okay, so you can do powder simulations also from starting from. So you can actually predict a theoretical molecule, and then of course you can see you can actually simulate a powder diffraction. Then of course you go for the experimental one. Of course you can verify that. Okay. And Linux Pro, as I told you, actually as I told you, this is actually a software which calculates crystal and molecular properties from multiple parameters of the electron density, which is derived from X-ray diffraction patterns. So from X-ray diffraction pattern, you go into the Fourier synthesis of it. You get the structure factor. Then you do another Fourier synthesis. You get charge density. You take the charge density at every single point in the unit cell. You convert them into several other things. Okay, so like an electron localization function. Electron localization function is something actually where you can actually predict where the orbitals are. Okay, one of I would say my one celebrated work was on germanium. So germanium is a one single atom. Of course, with the germanium crystal I took, and then of course we calculated charge density, but then we didn't know actually what actually we can do more on the molecule. So what we went on calculating the molecular properties, crystal properties and molecular properties, which can otherwise be calculated from quantum chemistry or quantum mechanics. Okay, so you need to have quantum mechanics to calculate all those parameters. Okay, where actually you will actually find out the electron localization function. When I say electron localization function, you start from the nucleus, and then of course you proceed along till the end of the nucleus. Okay, then of course at every single point where the orbit is located, okay, you will have a peak. You will have a peak like this. Okay, so I would say this is actually the K shell, this is L shell, M shell, and so on. Okay, so if you want to believe me, you have to believe me, of course, because I can be very sure of what I'm telling. So you can actually predict the positions of orbitals in an atom if you are really interested. And of course, we are actually interested in chemistry and chemical properties of molecules and so on. But then if you go into the details, the very details of an atom, okay, you can look into every single one of this. Okay, I'll take 2 more minutes and then I'll finish it off. Okay. Then of course, so this is actually what you call the trajectory. Okay, it's actually every single region, okay, encapsulates a particular atom. Okay, every single region encapsulates a particular region, or you can say when the atoms are put together, how the electron densities will actually have a shape. So these are actually borders within which the electrons of this particular atom actually lies. Okay, so the quantum mechanics never will allow the electrons to escape out of its domain. Okay, or the atomic basin. Okay, we call them as atomic basin. This is actually the atomic basin within which every electron is encapsulated. Okay, so you can actually get a picture of it. Okay, as I told you, actually we can actually see the properties evaluated by NX Pro. Total electron density, core valence electron densities can be separately evaluated. See, we talk about populations. Okay, so populations in core orbitals and population in valence orbitals. So suppose if you are interested in electron transfer, okay, you can look into the valence electron population, and of course you can finalize, you can say whether the electron transfer actually has happened between atoms or molecules and things like that. Okay, the deformation electron density, Laplacian electron density, the Coulombic inner crystal potential, gradient vector field that actually I shown in the last slide. Then the kinetic energy density, potential energy density, electronic energy density, electronic exchange energy density, and so on. Critical points. Critical points are basically the points which will define the type of bonding. Okay, I mean, we know about it in a better way. Of course, we will actually find out the critical point along the bond path between two atoms. We will actually find out the bond path. We will draw the bond path. We will find out the critical point where the inflection actually takes. I mean, that is actually the border. கரெக்டா பார்டர்ல அந்த ஆட்டத்தோட பார்டர்ல வந்து இந்த ஆட்டத்தோட பார்டர் பாயிண்ட் அந்த ஆட்டத்தோட பார்டர் பாயிண்ட். So that we will find out the point which is the border point, which is called a critical bond point. Okay, from that point, at that point, okay, looking at the charge density, I can tell you whether it is a sigma bond, whether it is a pi bond, whether it is a shared bond, okay, whether it is an whether it is a ionic bond or whether it's a covalent bond, okay, or whether it is a strongly correlated bond or anything. I can tell you all types of bonds from those information. Okay, and the information at that point is also very, very important, okay, for other calculations. Okay, so as I told you, electron localization function, we can actually locate where the electrons are, where the orbitals are from XRD. Okay, so Fermi momentum is a quantum parameter. Okay, and the electric first moment, second moments, the dipole moments, and whatever. Okay, okay. Now this is actually the last one. Okay, so which is actually the databases. Databases are where actually you can find out the information about the entire molecule. Okay, so you go for the molecule. Okay, you will get the information about the unit cell constants and everything, positions, everything. Then you get all the parameters that you want to calculate. Okay, you can get out of all these things. Okay, so PowBase is actually a powder diffraction database. JCPDS, you know about the JCPDS, that a repository of PDS is a repository of the powder databases. Okay. Then ICSD, inorganic crystal database is there. CCDC, there is a base is there. Minerals, you can find out minerals from American mineralogists. Crystallography open database is there. There is a database called X-ray data. Mineral list. Okay. Ethanol minerals. IUCN, the International Union for Crystallography Data. Okay. You can find almost all data from IUCR website and IUCR journals, then public sets. Okay, crystallographic information file. Okay, so if you want crystallographic information file, it is there. It is free. Everything is free. This is actually an ICSD database. This is actually a screenshot. Just type the formula. Okay, when you know the chemical formula and when you know the space group, if you know anything about unit cell, everything you will get. Okay. Or simply you put one input here, and then of course you will get many choices from there. Actually, you can select and then you can find out your own data. Okay, as I said, crystallography open database is there. Okay, see, you can search for the data. You can deposit data also. Okay, you can deposit your data also. Okay, so COD, NCD, CMD, wiki crystallography, many things are there. Protein structures are there in the protein data bank. Okay, so macromolecular crystallography group, actually they have a protein bank in Europe. Okay, see, most of the European databases are free. Most of the software come from Europe. Europe countries are free. Most of the softwares that come America are commercial. They need money. Europe doesn't want money. Okay, so this is actually another screenshot of American mineralogists. Just put the chemistry search. If you have a mineral that may have these three elements, then of course you will get the entire list of the thing. Okay, the other list is there. Okay, you can actually go for many databases. Okay, the list is not complete. Okay, so as I said, I'm just giving you a picture of a drop of a bigger ocean. The ocean is out there. You can explore. Okay. Okay. So to find a software, okay, what you have to do is you have to specify your need, the purpose of it. Okay, and what are actually the data that is available with you, and what are all the parameters you actually are looking into. So that is actually an first thing actually you have to decide to find a software. Okay, then you ask an expert. Okay? It's better I think you ask an expert. Okay? Because they will ultimately guide you in even in using the software also. Okay, a friend, and then of course you can internet. Okay, go to the you can go to the internet, you download it for free or pay and use. Okay, but whatever you do, you acknowledge in publications. Remember, when you are purchasing it, actually you don't need to acknowledge them. Okay, you don't need to acknowledge them, but then of course you have to give a reference of their works. That is very important. Okay, the Gaussian, actually we have a reference. Although we purchase it, actually we have to refer it. Okay, so thank you so much. I think I can finish it off. It's a very small introduction about the softwares here. Okay, so I think done with that, Javi ma'am. In case if you have any doubts or something, actually I can help you. Okay, maybe you can put your questions here. Okay, I have given a PDF of my presentation here. Okay, as I said, this is actually a drop-off version. I have given it to Dr. Janima. You can get it from her. Okay, or you can ask for them in your mail. Okay, so anything you want? Mama, are there any questions? Somebody interested in any calculations?
Yes, sir.
It's like, yes,
Some
Johnson.
people may be wanting to clarify. So we'll have the session open for discussions now. So the participants, you are encouraged to ask.
Please unmute them.
Please, you can ask your questions.
You can raise your hands also.
If you don't have if you don't have your mic properly working, you can use the chat box to post your questions.
Yeah.
Sir, good evening, sir.
Good evening.
Sir, nice. You are clearly explained about the software available software packages. Well and good. My doubt is, what are the data we require to run Jana 2006?
All you need is an intensity file. Okay, so when you have a raw intensity file, the Jana actually can refine it. Actually, the data reduction process can be done by Jana itself. Okay, there are some procedures by which actually you can reduce the data, and then of course you can go for structure refinement. After the structure refinement, you can go for the charge density determination. After the charge density determination, of course, you can go for multiple parameter determination. After the parameter determination, you can go for other calculations like quantum chemical calculations and so on. The list is a very big list, but you should start with the intensity data. Simple intensity data from any diffractometer is enough. Dr. Anselin is also there. I think she is very good at the Jana's software. Okay, so you can ask questions to her also. Yeah, please.
Sir, and one more question.
Yes, ma'am.
Suppose, is there any software is available to predict the structure based from PDB file? Because I'm having suppose if I'm having the structure based on the PDB, XYZ coordinate, is there any available software is available?
Are you talking about the protein structure or?
No, sir. No, sir. It's just a carbohydrate. Protein is very big now. So just I am asking about drug molecule, just like that.
Okay, drug molecule. Okay, so pharma. Okay.
Only I am having the PDB structure only, XYZ coordinate only. Is there any software to view free software? I am asking about the free software, sir.
Ma'am, actually the COD is there. There is as I told you, I think I shown you the softwares, actually I'll give you the COD is there, crystallography open database. This is actually managed by IUCN. See, several people actually come together to contribute, okay, to manage the entire website. Okay, this COD, okay, you can simply give the structure of it, and then of course you can get all the information about the thing. Okay, so you can actually make use of this COD. Okay, other softwares are there. Other softwares are. I'm not very familiar with other software. ICSC is there. Okay, so this is actually for mainly for inorganic compound. Okay, for organic, I think this is the best. As for my experience, okay, I would say. Okay.
Okay,
Yes,
sir.
ma'am.
Thank you.
Yeah. Yeah. Anshi ma'am, can you answer that Priya's question? Can you add some more information on that? Are you there?
Sir, if possible, kindly explain with your any one of the simple example to run any one of the software. Because just
Okay.
from your talk,
You
we
want me to
learned
run
about
this right now? I am not permitted.
Yes, sir.
I am not permitted here. Actually, Jemima ma'am, are you there? Can I go
Simple
for
example. Simple
can I
example
go
is
for
enough.
an
Sir. Just how to, because if we downloaded the Jana software, we don't know how to we give the input. That's why I'm asking.
no, actually, that is actually a very different one. I'm so sorry. Yeah, this is, you want to know the structure, or you want to run Dana software. The Dana for running.
Because what is the
Okay.
input we have?
Well, yeah, I understand. I understand your anxiety, but it takes it takes an initial setting up. Okay. You need to set up the data file. Okay. You have to make the data file. You have to create a folder. You put it there. You give a name, everything. You have to create symmetric cards. There are many things in the input file. You will have to do everything on that. Then you can take it to the Jana software. Okay, you can, as I said, you start using all the toolbar there. Then enter everything. Entering the initial data itself will take you at least an half an hour. Okay, then of course you can actually run.
Okay.
I think I'm not permitted to do that. Yeah. Here. Yes, ma'am. Thank you so much. Okay.
Okay,
Thanks for the good question. Yeah.
Thank you, sir.
Anybody else?
So I have a question, sir.
Oh my God. Thank you, ma'am.
Okay.
Don't
So
frighten me.
suppose I have a real lattice
Yes, ma'am.
where there is some vacancies or spaces available, like a
Okay.
tetrahedral
Yeah.
hole empty or an octahedral hole which is empty. So my
Yeah.
idea is if I wanted to incorporate a small atom that
Yeah.
can match into these holes,
Yeah.
it's just a theoretical imagination.
Yeah. Yes.
So is there any software which can generate the imaginary structure?
Ma'am, actually, you are talking about quantum chemistry software, ma'am. One thing is the Gaussian is there. There is a material software is there which is available. I don't know. I'm not getting that name. Okay. Avogadro is actually another software, but I have an apprehension that where I don't know whether we can actually have vacancies and filling up vacancies with a particular atom or something. Actually, you can create a plane of atoms. Okay, so you can actually put your own molecule there, and you can actually replace some of the atoms by some other elements. Okay, then you can run the program to find out the energy of it. Okay, whether it is chemically stable or not. Okay, so that can actually you can actually get from optimizing that particular molecule, optimizing the combination of the molecule. Okay, whether it is chemically possible to put that atom into that vacancy position or not. Okay, so those things will can actually be done. Then after that, after putting that atom into that place, okay, what will actually go to the chain of atoms? How the chain of atoms will actually change its structure in order to accommodate the new atom and all those things. Okay, so these things are basically quantum chemistry software. Mom, I didn't talk about all these things. These are all SRD software. Avogadro is there. There are some very good. I forgot that software name. Okay, sorry. Actually, I came across that
I
software in
worked on
secret.
a system called Mg2Si,
Okay, ma'am.
magnesium silicides.
Yes, ma'am.
And it is having a FCC lattice
Okay.
where you can find some tetrahedral holes empty, tetrahedral voids.
Okay.
So it's actually Mg2Si is a good thermoelectric material,
Okay.
magnesium silicide. So in addition to this thermoelectric property, suppose if you can put some small atoms like boron and put it into those voids, boron atom.
Yes.
It can rattle in that space. And it can increase the thermoelectric property of the material.
Okay.
That was the idea.
Yes.
Okay, but when we did the preparation, this compound is going on consuming boron. Boron actually it is going inside, but we could not see any lattice parameter difference.
Ma'am, yeah. See, okay. Please complete. Yeah.
And since boron is a small atom, we could not even identify its location in any XRD because there was no change in the XRD pattern of Mg2Si with the Mg2Si-B.
Ma'am, when you are doping an element into the solid, okay. So how much percentage of the actual atoms which are already there in the lattice is replaced is a big question. Okay. So suppose if you are replacing some 5% of atoms, okay, or 10% of atoms, or 20% of atoms, then you will never be able to see the effect of it. The effect can actually be seen only at the electron density population. See, at one particular point, atomic position, when you calculate the electron population, actually you will find out the combination of both the atoms together. Suppose, as I said, okay, Si is there, then you add boron. Okay, you take the atomic number of Si and the boron, and how much percentage if you are adding the boron with the Si. So if you are replacing 5% of the silicon atom by boron, okay, then Si 95% plus 5% of the boron atomic number Z, okay, that you have to add. So you will find out the total number. If this number matches with the electron density population found at that particular position, okay, then we can confirm that the boron is actually there. Boron is actually doped in the lattice. Otherwise, you will have to adjust the number. You will have to adjust the percentage. So that is how actually we do it. That is how the doping is understood. And similarly, suppose if there is a deficiency in the number of electrons at that particular position, okay, then we can say that some of these silicon positions are vacant. So vacancies are there. So it is actually a total effect that you get in X-ray effect, because it is not a single evaluation. It is actually an evaluation comes from different planes stacked together. So one plane, another plane, another plane, another plane. So everything stacked together. Okay, we have several planes. X-ray actually goes through every single plane, gets information out of it, then it gives you. So that is where actually it gives you information of the entire parallel planes. So that is actually one of the things, ma'am. Actually, if you want specific information which can happen on the surface of the material, then you should go for SEM or AFM technology, where actually you can see the replaced atom. So instead of the silicon atom, you will see boron there. So boron will be in different color and silicon will be in different color. And you will see different potential also, electrostatic potential. So you can map them. You can map the topology on the surface. But inside of it, when the atom goes inside, then it is very difficult. You can only see the electron population there, and then only you can confirm the atom is replaced by these many atoms this much percentage of atoms, or some are vacancies and so on. So that is the only way.
So if you are wanting to do this doping studies and identify the percentage of dopants in the lattice,
Yes, ma'am.
should we, what the parameter we have to inform when we are going to record the XRD?
Well,
Generally, we
ma'am,
take samples.
nothing. No, actually, unless, as I said, unless there is an expectation of a fluorescence effect, okay? Because as I said, copper is there. Okay? Suppose if you are doping copper, okay, on a material, and you are using a copper K alpha, or if you are using molybdenum for a molybdenum K alpha line, then that is a problem. Otherwise, you don't need to do anything, because there is no fluorescence effect can happen, and that will spoil the entire XRD experiment. So you don't need to say anything to those people. Okay, you simply tell them, actually, okay, we have a doped material and where this is actually the percentage, but they will not give you any, okay, they will actually give you the altered cell dimensions. Actually, suppose when you're doping a smaller atom, the lattice may shrink. The lattice may shrink, and it may give you smaller dimension. I mean, it may give you smaller units of dimension. Or if you are deliberately putting a bigger atom, forcing it on a lattice by replacing an atom, then of course the lattice may expand, so there will be a strain, and the lattice may expand. You will see those parameters in the refinement. You can actually very well understand that. Yes.
Okay, one more.
But you don't need to give it. Yes, ma'am.
From the user end, when we send the sample for X-ray, they ask for something called the scan range. What is the theta value you have to specify?
Scan range,
Scan rate also. So
and scan range should always be a long range if you want a large information. So see, that is why actually the geometry, the optics of the geometry of the photodiaphragmometer is very, very important to be understood. Okay? The counter can actually go through only in 180 degree of rotation, the maximum. But it will not go to 190 degree of rotation because of all the tubes, wires and everything. So there will be a free space where actually you can move freely over 120 degrees. So if you are going for 5 to 120 degree or at the maximum 145 degree, okay, you'll get the entire range of reflections. Okay, because more than 100 degree, of course, you will not get the considerable information out of it. So it is not necessary to go after 100 degree. Okay, so degrees. Okay, you can say the limit. You can go up to 145 degree also. You can go up to 145 degree also. From 5 degree to 145 degree in steps of 0.01 degree. In steps of 0.01. So when it is 0.01 degree, so it starts from 5 degree, then it counts again the extra photons at 5.01, then 5.02, it stays there for a while, it counts. Like that actually it goes on. So if you are diminishing the steps of it, then I think it is better. 5 to 120 degree with a step of 0.01. Yes, ma'am. There was another question that came in Akshaya, somewhere somebody was asking, I think, whether we can use some porous materials for X-ray. Please understand that porous materials are the materials which are having pores on the surface. And these pores are not only pores on the surface, it is a three-dimensional, it goes into the lattice. So there is no continuity of the atoms arranged there. So they are not in crystalline form. So actually you cannot use it for X-ray diffraction, one. And the thing is, the porous materials, I think as far as I understand, the porous materials are sheet of material, which are bigger in dimension. You don't need the bigger sheet for X-ray diffraction. You need a very small piece of 1 millimeter size. That is enough. If that 1 millimeter size itself is having some pores, very small pores, then I think it will not be useful for X-ray diffraction. They are not crystalline. Crystals need to have a good, well-surfaced one, polished surfaced one. and they need to have a longer arrangement of atoms okay, over a long range. Yeah, so that is not possible. Dear sir, informative and okay. I wanted to get a preliminary. I'm so sorry. Actually, I'm reading some questions here. Okay. I wanted to get preliminary idea before this workshop. I got what expected from. Okay. Oh, thank you. Thank you so much. Okay. Thank you so much. Can we take XRD porous solid material? No, I said. Then we have two methods of XRD instrumentation. One is vector rotation mode and the sample tray rotation mode, which is effective. Whichever is giving you good set of data, so that is effective. I mean, it depends on the instrument and the result. So please understand that it is not the mode in which the instrument is actually playing around. It is the result which is important. So whichever is giving you good results, that is effective. So you can actually try both the modes and you get the results. Okay? So whichever is good, please adopt that mode. So that is my answer. I think these are all some industrial based questions. Okay. So we don't need that. So that is what I try to understand. Okay. Okay. Thank you. Thank you, Accic. Okay. Bye.
I have one more.
Yes,
In
ma'am.
porous material, porous ordered materials,
Yes, ma'am.
we grind that compound finely.
It becomes powder. They are no longer porous now.
Yeah.
See, when you have a three-dimensional, porous material or porous material, when you have a three-dimensional material and there are pores, if you are grinding them into smaller size, into a nano size where the pores are disappearing, then it is simply a powder.
Powder material.
They are no longer, they are no longer crystalline. But the simple single the powders, okay, even in the nano form, okay, they are crystallized. So they can diffract. So you can use it for powder diffraction. But only the materials will actually give you every information, not the pores. Pores will not give you information. I think the pores can give you information only through electrical and optical properties, not XRD. Only big people are asking questions. So
Sir, I have a question.
Yeah. Thank you, Stefan.
So, X-ray diffraction, that is a unique and really a powerful technique. And we try to solve the structure based on the data that we get. And the other techniques like Maldi-Toff, mass spectrometry, and circular dichroism, if we have data of the same molecule, which are crystallized or studied with X-ray also, will those data from those techniques add strength to the analysis using X-ray, or X-ray itself will be enough for understanding the molecule better?
Well, yeah, thank you. That is where actually I told you. You should know actually what you are asking for, and you should know actually what you want. See, when you want only NMR or mass spectra of a particular molecule, then you go for, okay. As I told you, I mean, the parameter that you can actually evolve from XRD are tremendous actually, and the thing is, the inside out information of every single material can actually be gathered from XRD. So if you want those things, then I think you have to go for XRD. Otherwise, okay, I'm not good at mass spectra, NMR, IR spectra, and things like that. Okay, so the thing is, I don't know what actually they will actually offer. But as I know, NMR can give you a structure. Actually, the IR can give you a structure. XRD can also give you a structure. But apart from the structure, the mere structure of a molecule, XRD gives other information also, because it can actually you can actually go for charge density distribution of the molecule, and you can understand what is what. Okay, as I told you, see, Anselin is there. I think they have investigated some of the drug molecules. Okay, see, where actually you can see very simple region like the lone pair regions of oxygen. See, it's something I don't know whether you can actually visualize from NMR, mass spectra, or IR data. I think that is not possible. I don't think so. but you can actually see those lone pair regions of oxygen atom, okay, from XRD. Okay, so you can see different type of bonding. Okay, I think as I said, the sigma bonding, bi bonding, and every type of bonding actually you talk about can actually be visualized. It can be visualized from XRD. Suppose you can do the same thing by any other tools like mass spectra or NMR or IR. I think I don't know. You can go for that. But XRD
Because
is a
nowadays
yeah.
in the data bank, I see many entries coming in with structures solved with just NMR, and
Yeah.
apparently that appears like a substitute for X-ray diffraction, and that's the case with proteins which are moderately smaller, not with
Okay.
bigger. So, do you think X-ray will be having an added strength with other techniques, or uh, in the long
No,
run,
I don't know.
X-ray?
I'm asking. No, I want to know from Dr. Janima whether we can identify polymers from NMR data or mass spectra. Whether we
Yes,
can
sir.
distinguish between two polymers by means of NMR, IR,
Fragmentation
or
can be done in mass, but in IR you will
no.
get only the stretching frequencies. What are
Okay.
the functional groups present?
Yeah.
Uh,
See, but in XRD, you can see the different you can see the two different polymers. So one is twisting on one side, the other one is twisting on the other side. Okay. So you can actually why they are twisted and how they are actually arranged after going through different forms. Okay, can be seen, and you can actually see a step-by-step investigation of even phase transitions that can be done. That can be done under temperature range or pressure range in XR. Which atom is actually, which group of a set of atoms are actually involved in phase transition, where the bond actually is breaking, which one is breaking and which one is getting stronger, which one is becoming weaker. Everything you can understand from XR, right? Step-by-step analysis. I don't know whether you can do the same thing with mass spectra. Mass spectra, I don't think it's possible. IR, I don't know. NMR, I don't know.
Thank you, sir.
Yeah, thank you, Johnson. Yeah. Whether the synthesis of a particular sample will be reflected in the exactly, for example, reaction, temperature, pH. Okay. Now, so that is actually a good question. I think Sharmila actually, whether you are, suppose when you are synthesizing a material with a different solvent, okay, whether it is going to reflect on the final crystal, if the crystals are same, if the product is the same, you will not see anything. Okay, one. The second one is suppose, okay, the reaction temperatures is different, okay. If the molecules are same, the final product is same, then again you can't see any difference. But if there is any change in the structure, even a small change in the structure, okay, so that can be visualized, so that can be seen, so that can be understood from the XRD structure. Okay, then the pH of the sample, I mean whether in the synthesis process, whether you see the pH of the sample. See, if the pH of the pH of the solvent, okay, the pH of the solution, okay, or the solvent, okay, if it changes, if it incorporates any change in the final molecule, then only the XRD will see it. Otherwise, it will not see. So, any change, whether it's a temperature or a pH or any change, when that affects the final product, then only it will be reflected in XRD. Otherwise, you will not see anything at all.
Thank you, sir.
Yes, ma'am. Thank you.
Any more questions? Participants are encouraged to interact with the speaker.
Okay.
Do the
Yeah.
participants have any more questions? Okay. Before we conclude, we request few of the participants to come forward for a feedback session.
So participants, kindly give your feedback with your video on about the 3-day workshop. Can be any feedback so that we
Hello,
can,
ma'am.
yeah,
Yeah, Jamima, ma'am.
introduce
Myself.
yourself.
Yeah.
Yeah.
Hi, ma'am. Myself, Harida Baby from Cochin University of Science and Technology, Kerala. So, for the past 3 days, excluding Sunday, we have been having this wonderful session. And one thing that I wanted to mention was all the all the sessions were very thorough, very thorough. I mean, it was long, yes, but all the sessions were well thought out, and I mean, it was very clear that we needed it because all the details that we usually don't get in a class. I would rather say that we had a 3-day class crash course on X-ray techniques and the theory, everything. None of it was left out. All I could One suggestion that I would make is rather extend the days and keep these sessions short if possible, but I know there are limitations to that. I mean, not all of us have the time, but that would have, increased the attention span that we can keep on each class. That was one thing that I had issues to follow. Like after some time you tend to phase out of it, but these are things that we can't control when everything is online and all. But despite all that facts, it was a wonderful session. And I mean, these are techniques that, as a research scholar, these are techniques that we don't usually do every day, but which are very essential. And we might not know everything in detail, but this class for the past 3 days actually gave us an idea about, okay, what all things we can handle, what all things we have to take care in, preparing our samples, or what are the things that they do. Usually for us, what we do is we prepare a sample, like we synthesize something and then we take it to the external agent, where the samples undergo all this characterization techniques, and they just give us back the data. And we are at loss sometimes what to do with the data. But I am pretty sure all of us have gained a lot of insight into the minor details that we can handle and change and ask them to do while we are giving a sample. So thank you so much for the organizers and the American College Madurai. Thank you, ma'am, and all the professors who have given us their valuable time. So yeah, I hope everyone had a good time. I surely did. So thank you.
Thank you very much. Any others?
Ma'am, actually, I want to add one thing. Thank you, Harita, for mentioning it. Actually, many of the research scholars who are treating the sample with the help of with the XRG techniques and other things, they don't do anything other than just getting the data by from somebody, and then of course picturizing it, putting it in their paper, and then leaving it out. But remember, enormous information is there inside of it, and nobody actually wants to explore those things. Okay, so it's very as a crystallographer, I feel pained, of course, when somebody is mistreating XRD. So I think you have come up with with the open thing, actually, where actually you have mentioned the thing. Okay, of course. So I think for people beginning with the XRD techniques and other things, of course, they can actually use it in a very effective way. Okay? They can add substance to your paper. That is what I'm trying to say. See, your paper can get easily published if you can add more analysis with the XRD. Okay, thank you so much. Actually, something I wanted to add.
Any other feedback? PG students? Feel free to tell anything you want. UG students? Okay, so we are nearing 8 o'clock now. I think we need to take photos of all the participants. Saturday we tried, but many were not prepared, I think. Okay, so I would like to request everyone to switch on your video so that we can capture your faces. It will be a memory for us. So kindly, all participants, please switch on your video. We will take frame by frame the photos so that we can have it. Please. Thank you, thank you. Still many people. Please. Israel, sir.
Yes, ma'am.
Your video, sir. Yeah. Okay, Jansi, I think you can start taking.
Yeah, thank you so much.
Please keep your videos on till we ask you to switch it off.
I could see only 4 videos, ma'am.
Why? I could see many. 4 in a frame?
Oh, yes. Ma'am, only 4 videos only on in my laptop.
My God. I
Oh,
could
yes.
see.
Now they are coming. Oh, yes. Now they are
Yeah,
coming.
yeah. Maybe it's network connectivity problem.
But not all, ma'am. Only very few.
It's okay. I think maybe they are not prepared.
Okay. Now almost they are coming.
Yeah. Once you're finished, you tell us, Jansi.
Oh, okay, ma'am. I'm taking in a single screen only, ma'am.
Oh. Maybe you have to wait for some time.
Completed, ma'am. Thank you.
Completed?
Thank you all. Yes, ma'am.
Okay. Okay. Thank you very much. Johnson, um, just deliver the word of thanks.
Okay, it's my immense pleasure to deliver the vote of thanks on behalf of the organizing committee of this workshop. I, Johnson Christas, co-convener of this event, gladly deliver the word of thanks. The first vote of thanks is to God Almighty, our gracious Creator, for He has been the source of every blessing. Thanks to God Almighty in the name of Jesus for His unspeakable gift. On behalf of this American College Central Instrumentation Center and the organizing committee of this workshop, we thank our principal and secretary, Dr. Davamani Christopher, for his encouragement and support at every juncture. We thank our bursar, Dr. Dorothy Sheila, who has always been with us, encouraging us. Not only that, most of the time she joins us in executing every effort to organize events like this. And we thank each and every other authority and every member of the college Central Instrumentation Center. and we thank the heroes behind the screen whose efforts are not displayed here, without whose efforts this event would not have been possible. So we hope that we have learned so much on using X-rays to do more research. I explicitly thank the speakers, Dr. Sonadurai and Dr. Israel Samuel, for their precious time and their informative sessions. I thank all the participants from every arena of science and from various institutions across the country. The participants are really participating, and that's really encouraging for us to have more sessions like this. And I thank our coordinator, Dr. Jemima. So there's an opportunity for us to organize events like this. Ma'am often gives us an opportunity to put all the facilities accessible with the knowledge about it. Thank you, ma'am. So if I have missed anybody, please excuse. Thank you so much. Thanks to everyone.
A special word of gratitude to Dr. Israel. In fact, it has been a very smooth sail for us because the first 2 days it was really heavy dose for all the participants.
Oh, I
I
see.
okay,
This is a right
so
dose.
because he was a research scientist. Okay,
Yeah.
so from the scientist perspective, we were listening to, and you're a teacher. Okay, so you're a good teacher. So you taught us what actually a student can grasp. So from that point of view, you were talking. So really, it was very interesting, and I'm sure you would have put lot of effort in bringing out the vast information into a few slides. So thank you very much, sir, for sparing
Thank
your
you, ma'am.
time in
Thank you so much.
preparing this for this workshop. Thank you very much.
My pleasure. I'm privileged.
Yeah. And in
Thank you, ma'am.
addition, I wanted to thank Mrs. Jennifer and Dr. Jansi Rani because they were behind the screen and working for this workshop. And it was really, without their help, we could not have arranged it in a very short time. Okay, so thank you, both of you. And I have some informations like your certificates will come to you in another 2 or 3 days. So please give us some time so that we can get it in a correct manner. And the proceedings, it will reach your hands in another 2 weeks because we need to do a lot of compiling, addition, deletion. Okay, so please give us some time. So in another 2 weeks, you will get your proceedings in the e-copy form. Okay, so thank you all the participants, and we hope that we will meet again in another interesting workshop. Thank you very much. God bless you all.
Thank you.
Thank you.
Thank you so much. Thank you so much. Good night to you all.
Yeah, good night. Good night.
Thank you, sir. Thank you, ma'am.
Thank you, sir. Thank you, ma'am.
Thank you, ma'am.
Maybe Jansi, you can remove the participant.
Yes, ma'am. I too feel the same.
Yeah,
Okay, ma'am.
because I think. So we have completed by God's grace
Yes, ma'am.
big work done. So we should congratulate our own selves.
We should get
Thank you, ma'am.
the certificates ready, ma'am.
Yeah. Jennifer, will you design the certificates?
Oh, yes, ma'am.
Huh? ஸோ டிசைன் பண்ணிட்டு அண்ட் தென் 2 or 3 daysல டிஸ்பர்ஸ் பண்ணிடலாமாப்பா ஜான்சி?
Sure, ma'am.
ஓகே. அண்ட் இந்த இது ப்ரொசீடிங்ஸ்க்கு என்ன பண்றது? ஜான்சன் மெட்டீரியல் 2 weeks டைம் கேட்டிருக்கேன், முடிச்சிடலாமா?
கொடுக்கலாம் மேம். நான் ஏற்கனவே ஒரு ரஃப் காப்பி அனுப்பிட்டேன். ஐ வில் டூ ஸ்பிட் அண்ட் பாலிஷ் நவ். அதுக்கப்புறம் அவங்க கொடுத்த கண்டென்ட்டையும் எடுத்து வச்சுட்டு we'll go for aligning everything, putting in there. 2 weeks is an ample time for us. I think we don't have to wait till 2 weeks. And I apologize. Okay, we'll definitely send it, ma'am.
Yeah.
And sorry, John J. ma'am and Jennifer ma'am, I did not mention you by your names when I start the word of mouth. Please excuse me.
It's not a problem, sir.
You did so much of work.
penalty கொடுத்துருவோம் ஜான்சன்.
அப்பலாம் எதுவுமே யோசிக்கல சார்.
I think somebody has entered. Santosh Kumar.
No,
Okay.
the program over.
Okay. So thank you very much. So we will meet again when we again have some other work. But by the time you please finish off the certificates and the proceedings, okay? Case and the proceedings, okay?
Ma'am, how many photographs and the screenshot pages required for the proceedings, ma'am?
We can give as many as we want because it is only an e-copy.
Okay, ma'am.
So participants one list and then speakers, resource personக்கு வந்து ஒரு ஆளுக்கு 2 samples-க்கு 2 for each.
Okay, ma'am.
talk. அப்புறம் பர்சா ஃபர்ஸ்ட் யாரு சாப்ளினோட ப்ரேயர்.
Actually, chaplain sir, he does not appear in the video, ma'am.
ஓ சரி, ஓகே. அப்ப பிரின்சிபல் ஸ்டார்ட் பண்ணலாம். பிரின்சிபல் அந்த மாதிரி அந்த ஈவெண்ட்டை கேப்சர் பண்ற மாதிரி ஒரு சீக்வென்ஸ் தான். 3 days ஈவெண்ட் நம்ம கேப்சர் பண்ற மாதிரி அந்த நம்மளோட அந்த ப்ரொசீடிங்கை வந்து டிஸ்ப்ளே பண்ணது.
ஓகே.
அந்த இது ஸோ அந்த மாதிரி கேப்சர் பண்ற மாதிரி போட்டுட்டு ஃபியூ போட்டோஸ்.
ஓகே,
அதோட முடிச்சிடலாம். ஓகே.
Come and just push the door.
Okay. So if